Okay, so for an isobaric process, the work equation simplifies quite nicely. We have a special equation that works for the heat. These equations work for the thermal energy. This equation works to relate all three together. Okay? You're really giving me a complex back there. These equations right here are unique to the isobaric process. You cannot use these equations if your process is not isobaric. They won't work. Well, I guess you can't use them accurately. You won't get a right answer if you try to use them. These equations work for any process. These aren't unique to any of them. So these will work for isobaric, they'll work for isochoric, they'll work for isothermal, so forth. These equations are specific to isobaric. Isochoric. Our isochoric process is the one where the volume is held constant. On a PV diagram, it was the vertical line. What can you tell me about the work if the volume is held constant? For example, if I stand here and push on the wall as hard as I can, how much work am I doing on the wall? Absolutely none. Why? It's not going anywhere. The wall would have to physically move in order for me to do work on it. If the volume is not changing, so if we have a bicycle pump and we're pushing as hard as we possibly can, but the piston isn't moving, how much work is being done? Zero. On the gas, specifically. In an isochoric process, the work is zero. By the way, if work is zero, then Q has to equal delta E thermal. So Q is equal to delta E thermal for an isochoric process. We do have, actually, it's the same equation. We write it as this: the Q is equal to N times CV delta T, where CV is 3/2 R, for monatomic gas. And 5/2 R for a diatomic gas. But according to the first law of thermodynamics, our top equation there, Q has to equal delta E thermal. Bless you. In the test notes, make sure you look at the test notes, but in the test notes we have the equations that are applicable to each process listed. Isothermal process is the one where temperature is held constant. If temperature is held constant, what can you tell me about the change in thermal energy? The change in thermal energy. It has to be zero. Delta T would be zero, because the final temperature is the same as the initial temperature. Delta E thermal is zero for an isothermal process. That means Q plus W has to be zero. So Q is equal to negative W, or W is equal to negative Q, whichever way you want to write it. Now the work term. Work is the negative integral of pressure with respect to volume. In an isothermal process, if the pressure changes, the volume also changes. And vice versa. Temperature is staying constant. So we need to actually integrate here. But we can't integrate yet. We need to integrate with volume being our variable, so we need to write pressure in terms of volume. We need to know how pressure and volume are related so that we can integrate with respect to volume. Okay? It doesn't become P delta V, because P is not constant. The pressure is going to change. So how can we relate pressure to volume? It's easy, really easy. How do pressure and volume relate?
CP over CV equals gamma.
Right? Our limits are going to be from some initial volume to some final volume. The nRT are all constants. They can come out of the integral sign. What's the integral of 1 over v with respect to v? Natural log. So we get natural log of v final minus natural log of v initial. If you remember, the natural log of one quantity minus the natural log of another quantity is the same as the natural log of the first one over the second one. So that is our work term. If you have an isothermal process, the work is equal to negative nRT, natural log of the final volume over the initial volume. There's no special Q equation like we had for the isobaric and isochoric processes. But that's okay because we know Q and W have to add to 0. So if you can find the work, you can find the Q. Now, an adiabatic process was one of the types of process that fell under that iso stuff category. Just the number of moles that are held constant. The pressure, volume, and temperature can all change. The one thing that characterizes an adiabatic process, it is defined as a process in which Q is equal to 0. So there is no energy exchange between the system and its surroundings due to temperature differences. That means if Q is equal to 0, then work has to equal the change in thermal energy. It's not very easy to find work by integrating the pressure with respect to the volume, but it is easy to find the change in thermal energy because those equations over there still apply. So if you can find the change in thermal energy, you automatically know how much work has been done. Now we have one other unique little equation. We get a relationship between pressure and volume. Pressure 1 times volume 1 to the gamma power. Volume is the only one to the power, not pressure. So pressure is normal, volume to the gamma power, that has to stay constant. So that means P1 V1 to the gamma power has to equal P2 V2 to the gamma power. Gamma always on here. Gamma is the ratio, I have to double check, I'll tell you right. It's an ugly gamma. Gamma is the ratio of the molar specific heat at constant pressure over the molar specific heat at constant volume. Okay. Do you have a question? Okay. So for a monatomic gas, Cp is 5/2 R, Cv is 3/2 R. If we take 5/2 R over 3/2 R, the halves and the R's cancel. Get 5/3. For a diatomic gas, 7/2 over 5/2, so 7/5. Now these Cp, Cv, gamma values are all in the test notes as well. I don't expect you to remember what all the little values are. They are in the test notes.